Hello, everyone. Welcome to our third press conference of today on giant seafloor craters and thriving fauna, methane, seepage in the Arctic. And we'll have two presentations, as always, by the speakers, and then we'll open the floor for questions from journalists. And taking part in this press conference, we have two PhD candidates from the Center for Arctic as Hydrate, Environment and Climate at the Arctic University of Norway. And they are Malin Våge and Emily Ostrom. And I'll just hand over to them. Malin, you can start.
Yeah, thank you. So I will be talking about large craters found on the bottom of the ocean floor in the Barents Sea that are evidences of massive releases from the very efficient climate gas methane related to melting of gas hydrates or methane ice. And methane ice is basically gas trapped in a cage of the methane gas. And it's also referred to as the ice that burns, as you can see here. A video taken from one of our field trips. Yeah. In cage, we focus on methane releases related to melting of gas hydrates and its impact on the marine environment and global climate systems. And I am a geophysicist in cage and work in the sub-seabed reservoirs. So this is a map of the Arctic with a zoom in of the western Barents Sea. The large trough you see here is the Bear Island Trough, and on the northern side of this trough, about 100 craters exist on the seafloor in a water depth of about 300 to 350 meters. These craters are currently a research focus for several researchers in cage, and I am using a technique that's called 3D seismic, which have, among other data, given me this 3D picture of the seafloor covering about 15 of these craters, ranging in size from 150 meters to 1 kilometers wide and down to 40 meters deep. In this map you see, or the red colors here are the most elevated parts and the purple are the deeper parts. And these craters are ancient futures remains from the last ice age for about 20,000 years ago. At that time, the Barents Sea were entirely covered by ice, as you can see here in the map, which led to a high pressure on the current seafloor in the area, which then led to accumulation of gas hydrates, which are very dependent on high pressure and low temperatures, which then led to formation of these of this very thick zone of hydrates. But when the pressure released and as the ice retreated, the gas hydrate started to destabilize and release gas, which eventually led to formation of these craters. But as you also can see in this map is that we have these top positive features or mounds that we also call hydrate-related pingos. And these are also associated with accumulation of gas hydrates and a buildup of gas pressure from below. So now I will, this area here is still continuously leaking gas today, and it's located on the limit for gas hydrates, or for the limit for the stability zone for the gas hydrates. For gas hydrates to be stable, and it represents one of these hotspots for methane release in the Arctic today. And I will now show you how we can see that in the 3D seismic data. So this is a little video me and a colleague made in front of this conference. So moving into the area. So as I said, the water depth here is about 300 to 350 meters deep. And the red colors, again, on the seafloor, the more elevated parts, and the purple are the deeper parts. So here you see the seafloor again. And the seafloor will soon fade away, and the structures underneath in the subsurface will appear. And these structures are faults or fractures, which basically are breaks in the continuity of the rocks, which I will go a little further into. Here, the Golden Gate Bridge is used as a size reference, about 2.7 kilometers wide. And if I stop there a little, as you see here, you have these stronger reflections underneath the craters, and these are interpreted to be shallow accumulations of gas, but also gas hydrates. And you also see traces of these vertical structures that are these faults, and they are, I can just go take it on a little, and they are often or situated directly underneath the craters, or just on the side, and represent pathways for the rising gas. So, yeah, that was basically it. So, but how do we really know that, or what other evidences do we have that these craters are formed by massive blowouts of methane? We can, for example, take a look on the seafloor in the area, which basically consists of angular slabs of siltstone and claystone, very abnormal from the area around, which is basically flat. So these slabs of rocks have, or are assumed to have come up, broken apart, and come up with these explosions. And I also included this image to highlight that the craters are incised in a hard substrate or a hard bedrock, and obviously it requires a lot more power to cause a crater in hard rocks than in soft sediments. So my conclusions so far is that these large craters exist, and hydrate-related mounds exist in the central Barents Sea, and they show evidence of a massive release of the climate gas methane. And in the 3D seismic, we see accumulations of shallow gas or free gas and gas hydrates underneath the craters and pingos. Seabed structures exist also in the area that show evidence of pathways for this gas in the past and also at present time. Why should we really study these features? Well, an enormous amount of methane gas is locked up below the seafloor in continental margins and under ice sheets worldwide. And we don't know what impact the temperature rise on Earth will have, or what causes. Yeah, we do not know how similar blowouts of methane will happen in the future as a cause of temperature rise, but we do know that huge explosions and rapid releases of the climate gas have happened in the past. And in a lesser scale, this has already started to happen. And of course, I refer to the craters that recently have been forming in Siberia, on a little lesser scale, related to melting of permafrost as a cause of temperature rise. Thank you.
Okay, then I continue. As you heard, my name is Emily, and today I will tell a short story for you about a biological oasis in the darkness of the Arctic Ocean. So I'm also from the Center of Excellence in Norway, CAGE, which has the interest to look at the fate of methane from the subseabed into the water column and all the way to the atmosphere. And I'm interested to see how cold seep environments are influencing seafloor communities in the Arctic. And my focus lies here on the seabed, and I'm interested to look how the animal responses. So the key message for this presentation is that we have an aggregation of larger animals called megafauna around features related to methane seepage. The infaunal community, referring to the animals living inside the sediment, is diverse and flourish at the seep. And we can see that the methane seepage form a biological oasis at the deep Arctic seafloor. But first, before I go through any details, we have to clarify a few things. As you all know, most life on Earth are dependent on the sunlight. But at the ecosystems that I study, no sunlight is reaching these great depths. Instead, we have another processes that occur called chemosynthesis. And in this process, we have different kind of chemical compounds that serve as the source, the main source of energy instead of the sunlight. And on these places where we have chemosynthesis or where methane escapes from the seafloor, these sites are also known as cold seeps. So we have investigated cold seeps in the Arctic with this piece of equipment. As you can see here, it's called a tow cam. It's a camera-guided multi-core and CTD. And this was developed through a collaboration between CAGE and Woodsole Oceanographic Institute in US. And the camera was that we used was placed in the front on this equipment. So I would like to show you a few images of the seafloor that we have taken with this camera. This photo here shows you a typical, or is representing a typical normal conventional Arctic featureless seafloor below 1,000 meters of water depth. And keep in mind that we are in the Arctic and it's dark and it's cold at these great depths. But now I would like to take you on a trip to a different place. We are still west of Svalbard in the high Arctic at 79 degrees north at 1,200 meters of water depth. And this place is called Vesnesa Ridge. And here you can see the ridge up here. And on this ridge we also have several different depressions, pockmarks. And on this ridge we have vast emissions of methane that emerge from the seafloor. And you can see these giant plumes stretching up from the seafloor more than 800 meters high. And here on Vesnesa Ridge, it's very clear that the methane really impacts the local animal life here. So we took several thousand images with this tow cam that I showed you earlier on the seafloor around Vesnesa Ridge. And we have seen that where we have this emission of methane, we have large formation of carbonate reef structured at below 1,000 meters of water depth. So you can see the carbonates here on the picture. Let's see the carbonates here. And we also have microbial mats, these whiter or bluish patches on the seafloor. And around these carbonates and the microbial mats, we have identified a large set of different kind of animals aggregating around these features. We have, for instance, different kind of fishes, sea spiders crawling on the carbonates, clams and snails, starfish and skates. Here is another picture showing you how it can look like where we have this seepage. And we can see this big patch of microbial mat, and we have tiny small fishes lying around these microbial mat. And over here we have 2 sea spider crawling around on the carbonate. And it's quite clear that methane generates an oasis effect where a lot of different animals gather for food, shelter and structure. Here I have also highlighted different kind of fish that we have identified around the carbonate reef. And I don't know if you can see the skate here hiding in the sediment. So this is also another picture how the seafloor can look like where we have the methane seepage. And this picture here, for me, it looks like a meadow on the seafloor. But this meadow is not composed by grass as it would be on land. This meadow is instead made of thousands of tiny tube worms getting their food and nutrition from methane seepage by help of tiny microbes that lives inside of them. And here you can see an example of this type of tube worms. They are called siboglinids, and they are completely dependent on methane for their nutrition since they lack both mouth, gut and intestines. So we can clearly see that the methane seepage as Vesnessa creates a biological oasis where the carbonates provides a reef structure and the methane generates food through different kind of biochemical processes. And this makes the surrounding seafloor looking like a desert compared to the seep site at Vesnessa Ridge. Thank you.
Thank you very much to both of you for presenting to us your fascinating research, and we'll now open the floor for questions. Are there any questions from here in the room?
Andy Coghlan, New Scientist. That was fascinating from both of you. Thank you very much. I mean, how unique are these ones in the Barents Sea compared with other seeps all around the world? I mean, is what you're seeing completely unique, or? And one other quick question: have there been any explosions in recent times, and what happened if there were any?
So I guess the first question is for you. Or so you were meaning you were referring to the oasis of life around that for the first questions, right?
Well, both. Are they two different?
It's 2 different sites.
Right.
Yeah.
Okay.
It's 2 different sites.
Okay. Well, first of all, the actual the craters, are they unique? Is there anything like them anywhere in the world?
The craters in this area are unique, considering their size and that they are actually incised in hard bedrocks. There are also evidence of craters like this outside New Zealand, with the range of a kilometer range. That also has been related to the same methane release from
So is your investigation and the things you've told us about, is that the first time, is this the first stuff we're learning about them?
No, this was discovered in the about 20 years ago.
Oh, really?
And yeah, so it has been some research papers 20 years ago, but obviously the equipment we use today are much better and much more, or like we can say, we're able now hopefully to say a little bit more about the formation and how these craters evolved. and what is happening in the area now.
And is that published?
It's published, yeah.
Yeah, right.
I can give you the articles.
And what about the oasis? Is there anything like that anywhere else in the Arctic or?
So it's quite common in these around these cold seeps to see an aggregation of animals connected to the seepage from the seafloor, connected to different kind of chemicals. But for sure, there is a huge lack of information about what's going on in the Arctic, and this can also be related to that there is a lot of things happening in the Arctic right now. With increasing temperatures and so on. So I think it's not so often that we have the chance to see the seafloor using cameras. I mean, the lack of information is very the information that we know about the Arctic is very limited. So this I don't think this has been seen as far north before.
And is your stuff published all about the oases?
It's not published yet, but it's in preparation.
Oh, okay.
Hi, very, very interesting presentations. Thank you. Marlo Hood with AFP. When we're looking at major drivers of climate change, seems to me that methane hydrates is the sort of scary feedback mechanism that doesn't get talked about. Is that because we don't know a little bit much about it? I noticed you didn't really, you said there's a lot there, but you didn't quantify it. Do we have any idea what the potential is there for the release of methane? And looking back over geological time, when is the last time that we had sort of massive eruptions or explosions of the kind that you're talking about, and what were the conditions that caused those?
So the major drivers for melting of gas hydrates are, or melting of gas hydrates are or associated with a release of pressure or temperature. When we go back, the last, or we like our during the last glacial maximum, we had all these massive ice sheets around that I said that, which led to a large accumulation of gas hydrates beneath them. And after, when the ice started to retrieve and the pressure released, that led to destabilization of hydrates all around the world underneath the former ice sheets. So that's sort of one of the times that like one of the last times I assume that this were like a major problem, that as we see now, that when the temperature increase and the melting of the current ice sheets, this can potentially, I assume, lead to or can lead to similar events.
So you're saying that would have been what happened starting 20,000 years ago, going into the Holocene. Did it stop at some point, and if so, why? Why hasn't it just been continuous since we've been in a warming or a relatively warm period for the last 11, 12,000 years?
I do see your questions, but like these craters are like evidence of single, or like it's just a focused area where methane has rapidly released, and like this release of methane gas is going on around on the continental margins still, but the most sensitive places are on the limit of the stability zones of the maybe Alexei or Jürgen is a better person to answer this questions. No.
Very briefly,
Yeah. Thanks.
today, yeah, I'm Jürgen Mienert. I'm the director of the Center of Excellence, CAGE. We see since the last deglaciation this as a continuing process, and there are some more catastrophic events in between, particularly in areas in the Barents Sea, but also in Siberia, around the northern US continental margin we see it, Beaufort Sea, and one can expect, if you do a projection into the future, that with an increase of global warming, key areas would be Greenland and Antarctica, where we should keep an eye on the processes.
I'm Anna Govorova, Russian newsmaking agency. I would like to ask you, what is the size of such microbial mats, and did you study how diversity changes during some period of time, diversity of organisms, and did you study the methanogenic bacteria which are living there?
So let me show this picture again. Yeah, as you can see, we have on the photos we saw different types of microbial mats. Some of them were larger, some of them were really, really small. This one, I would say, is quite large, what we saw in the pictures. This two lasers here, or you have the scale here, refers to 20 centimeters, so you can estimate the size of the mat. I am focusing on the megafauna, the larger animals, and or macrofauna, also the larger animals, animals larger than 0.5 centimeters. So my focus do not lie on the microbes. We have other researchers focusing on the microbial activity, looking into the methanotrophs and sulfur bacteria. So unfortunately, I cannot answer questions about the microbes in detail.
Thank you. Are there any additional questions?
Just a question for Emily. Is this what life would look like on the ocean floor of Europa or Enceladus?
Yeah, that's a good question. I have no idea, honestly. I try to focus on what's going on this planet and below the sea surface, and I think we need to know what's going on in these great depths before we start exploring things outside the planet Earth. It's my personal opinion.
Are there any additional questions? I apologize for those watching online. It seems we had some slight issues with the web streaming, which hopefully are okay now. But we still have time for an additional question if anyone has it. If not, we'll finish here. Thanks again very much for your presentations. You're more than welcome to approach our speakers, and our next press conference is tomorrow at 12. Thank you.